Okay, we're going to take a look at the first consequences of the fundamental theorem of similarity based on our last lesson that describes what the fundamental theorem of similarity is. So for this lesson, you're going to need graph paper for the examples and a ruler. So just to review the fundamental theorem of similarity, given a dilation with a center O and a scale factor R, then for any 2 points P and Q in the plane, so that O, P, and Q are not collinear, the lines PQ and P', Q' are parallel, where P' is equal to the dilation of P and Q' is equal to the dilation of Q, and furthermore, the length of P', Q' is equal to the scale factor times the length of PQ. So in other words, the FTS states that given a dilation from center O and points P and Q, which means point O, P, Q are not on the same line, the segments formed when you connect P to Q and P' to Q' are parallel. So more surprising is the fact that the segment PQ, even though it was not dilated as points P and Q were, dilates to segment P', Q'. And the length of P', Q' is the length of PQ multiplied by the scale factor. So the converse of this is also true. That is, if you have two parallel lines, PQ and P', Q', and that they are related by a scale factor R, then from the center O, P', which is a dilation of P, and Q', which is a dilation of Q, and the length of OP' is equal to the scale factor of OP, and the length of OQ' is equal to the scale factor times the length of OQ. So just a little bit about converses. The converse of a theorem begins with the conclusion and produces the hypothesis. FTS concludes that lines are parallel and the length of P', Q' is the length of PQ multiplied by the scale factor. The converse of FTS begins with the statement that the lines are parallel and the length of P', Q' is the length of PQ multiplied by the scale factor. It ends with us knowing that points P' and Q' are dilations of points P and Q by a scale factor R, and their respective segments, OP' and OQ', have lengths that are the scale factor multiplied by the original lengths of OP and OQ. So here's some more examples of converses. If it is raining, then I have an umbrella, and its converse, if I have an umbrella, then it is raining. Well, in this case, the converse is not necessarily true. An example where the converse is true can be if we turn the faucet on, then water comes out. And the converse is if water comes out, then the faucet is on. The converse of the theorem is basically the work we did in the last lesson, but backwards. In the last lesson, we knew about dilated points and found out that the segments between the points P and Q and their dilations P', Q', were dilated according to the same scale factor, that is, the length of P', Q' is equal to the scale factor times the length of PQ. We also discovered that the lines containing those segments were parallel. For example, PQ was parallel to P', Q'. The converse states that if we are given parallel lines, PQ and P', Q', where the segment PQ in one line is dilated by a scale factor R to a segment P', Q' in the other line. With that knowledge, we can say something about the center of dilation and the relationship between the segments OP' and OP, as well as segments OQ' and OQ. Make a conjecture about the relationship between OP' and OP, as well as OQ' and OQ. All right, let's go ahead and try exercise 1. In exercise 1, you're given the diagram where you have PQ, the line segments PQ, and P prime Q prime. And they have been dilated by a scale factor of PQ. The length of PQ is 5 centimeters and the length of P prime Q prime is 10 centimeters. So determine a scale factor. And according to this, the scale factor would be 2. Because if PQ is your original, P prime Q prime is enlarged, which means it has to be greater than 1. So locate the center of dilation, measure the segments to verify that OP, the length of OP prime is equal to the scale factor times the length of OP, and that the length of OQ prime is equal to the scale factor times the length of OQ. And when you do that, you should have gotten 2 and 3. 2 times 3 is 6. And over here you have 2 times 4 is 8, and 8 equals 8. Now that we know FTS and the converse of FTS in terms of dilations, we will practice using them to find the coordinates of points and dilated points on a plane. And we're going to begin with some simple problems. So in the diagram we have a center O and a ray OA. We want to find the coordinates of point A prime. We are given that the scale factor of dilation is R equals 2. So to find A prime, we could use a ruler or compass to measure the length of OA. But now that we know about FTS, we can do this another way. First, we should look for parallel lines that will help us locate A prime. How can we use the coordinate plane to ensure parallel lines? Well, we could use the vertical or horizontal lines of the coordinate plane to ensure lines are parallel. The coordinate plane is set up so that the lines never intersect. You could also think of those lines as translations of the x-axis and the y-axis. Therefore, we are guaranteed to have parallel lines. So let's use the x-axis as one of our rays. Notice that it is in red now, down here at the bottom. Where should we place a point B on the ray along the x-axis? Well, since we are using the lines on the coordinate plane to verify parallelism, we should place a point directly below point A on the x-axis. So point B should be at 5, 0. This is beginning to look like the activity we did in lesson 4. We know that the scale factor is R equals 2. Where should we put point B prime? So if this is scale factor of 2 and B is at 5, then if we multiply it by 2, it would be the fact that we would put B prime at 10, 0. So if the length of OB is 5, therefore OB prime would be 2 times 5. So here is our point. Here is our line length O to B, and here's our line length O to B prime, which is going to be at 10. So now that we know the location of B prime using FTS, what do we expect to be true about the lines containing segments AB and AB prime, or A prime B prime? We expect the lines containing these segments to be parallel. So then what would be the location of A prime? Well, point A prime will be located at 10, 4. So could point A prime be located anywhere else? Specifically, could we have a different x coordinate? Why or why not? Well, no, point A prime must be at 10, 4. If it had been another x coordinate, then lines AB and A prime B prime would not be parallel. So going back to this, if it would be anything other than that, if it would be here or anywhere connecting these lines, then this line would not be parallel to A prime B prime. So the only way it can be parallel is if the point is at 4. So could A prime be located at another location that has 10 as its x-coordinate? For example, could A prime be 10, 5? Why or why not? Well, now point A prime must be at 10, 4 by definition of dilation. If a point A is dilated from center O, then the dilated point must be on the ray OA, making points OA and A prime collinear. If A prime were at 10, 5, or at any other coordinate other than 10, 4, then the points OA and A prime would not be collinear. Alright, let's take a look at exercise 2. Go ahead and you should have this done. Again, starting with A, you create a point B on the x-axis and dilate it, and then from that you could find A prime. So the location of A prime is 12, 12. Alright, example 2 on your graph paper or math journal. Go ahead and copy this example down before continuing. So in the diagram we have a center O and a ray OA. We're given that the scale factor of dilation is 11 over 7. We want to find the precise coordinates of A prime. Based on our previous work, we know exactly how to begin. So we're going to draw a ray OB along the x-axis and mark a point B directly below point A on ray OB. The question is now, how do we locate B prime? Think about our work from lesson 4. In lesson 4, we counted lines to determine the scale factor. Given the scale factor, we know that point B should be exactly 7 lines from the center O, and that the dilated point B prime should be exactly 11 lines from the center. Therefore, B prime is located at 11, 0. So now that we know the location of B prime, where will we find A prime? Well, point A prime will be at the intersection of the ray OA prime and the line A prime B prime, which must be parallel to AB. Now that we know where A prime is, we need to find the precise coordinates of it. The x coordinate is easy, but how can we find the y coordinate? Well, the y coordinate will be the exact length of the segment of the length A prime B prime. To find that length, we can use what we know about the length of AB and the scale factor, since the length of A prime B prime is equal to the scale factor times the length of AB. So the length of A prime B prime will give us the y coordinate. Then the length of A prime B prime is equal to 11/7 times 6, which gives us 66/7, which is approximately 9 4/10. So that means the location of A prime is at 11, 9 4/10. Alright, go ahead and try exercise 3 and then continue the video when you are finished. Alright, you should have the following. The x-coordinate of A prime is 5, and that means you find the coordinate of length of segment A prime B prime, which is 5/12 times 8, which is approximately 3 3/10. So the location of A prime is at 5, 3 3/10. Alright, let's do example 3. In the diagram on the next slide, we have a center O and rays OA and OB. We are given that the scale factor of dilation is 5 over 8. We want to find the precise coordinates of points A prime and B prime. So go ahead and copy this down on your graph paper before continuing. Alright, so describing what we should do. We want to draw a ray OC along the x-axis and mark a point C directly below point A on the ray OC. Based on our work in lesson 4 and our knowledge of FTS, we know that the points B and B prime along ray OB enjoy the same properties we have been using in the last few problems. So let's begin by finding the coordinates of A prime. What should we do first? Well, first we need to place the points a prime, b prime, c prime on their respective rays by using the scale factor. Since the scale factor is r equals 5 over 8, then a prime, b prime, and c prime will have an x-coordinate of 5. Also, it is 5 lines from the center. So let's first find the coordinates of a prime. What do we need to do to find the x-coordinate of a prime? Well, the y-coordinate of a prime will be the length of the segment a prime, c prime. We can calculate that length by using what we know about the segment AC and the scale factor. So the y-coordinate of a prime is the length of a prime, c prime, which is equal to the scale factor times the length of AC, and that would be 5/8 times 9, or approximately 5 6/10. So that means the location of a prime is at 5, 5 6/10. Now find the y-coordinate of b prime. The y-coordinate of b prime is the length of b prime, c prime. So that means, using our dilation definition, 5/8 times 4 is going to be approximately, or is going to be equal to 2 5/10. So the location of b prime is 5, 2 5/10. All right, let's wrap this up. So we experimentally verified the converse of FTS. That is, if we are given parallel lines, PQ and P prime, Q prime, and we know the definition of dilation, then we know from a center O, P prime, which is the dilation of P, and Q prime, which is the dilation of Q, and our definition of dilation. In other words, if we are given parallel lines, and we know the length of P prime, Q prime is equal to P cubed multiplied by the scale factor, then we also know that the lengths of OP prime is equal to OP multiplied by the scale factor, and we know that the length of OQ prime is equal to the length of OQ multiplied by the scale factor. We also know how to use FTS to find the coordinates of dilated points, even if the dilated point is not on an intersection of graph lines. All right, we'll see you in class. First, we need to place the points a prime, b prime, and c prime on their respective rays by using the scale factor. Since the scale factor is r equals 5 over 8, then a prime, b prime, and c prime will have an x-coordinate of 5. Also, it is 5 lines from the center. Let's first find the coordinates of a prime. What do you need to do to find the x-coordinate of a prime? Well, the y-coordinate of a prime will be the length of the segment a prime, c prime. We can calculate that length by using what we know about the segment AC and the scale factor. So the y-coordinate of a prime is the length of a prime c prime, and or equal to the length of AC times the scale factor. So that means that we would take 5/8 times 9, and when we get 45/8, that is approximately 5.6. So that means the location of a prime is 5, 5 6/10. So now, use that same method, find the y-coordinate of b prime. Well, the y-coordinate of b prime is the length of b prime, c prime. So that means when you use the FTS, it would be 5/8 times 4, which gives you 20 over 8, or 2.5. So the location of b prime is 4, 2 5/10. All right, let's go ahead and wrap this up. So we experimentally verified the converse of FTS. That is, if we are given parallel lines, PQ and P prime, Q prime, and we know that FTS, that if we multiply the scale factor by the original length, we will get the dilated length. We know that from a center O, P prime is the dilation of P, Q prime is the dilation of Q, and so on and so forth. In other words, if we are given parallel lines, PQ and P prime, Q prime, and we know the length of PQ, P prime, Q prime is equal to PQ multiplied by the scale factor, We also know that the length of OP prime is equal to OP multiplied by the scale factor, and that the length of OQ prime is equal to OQ multiplied by the same scale factor. All right, we'll see you in class.